Steam Generation Part 3B.
You are watching Shoaib View channel. This is the Part 3B and continuing the Part 3 in which I discussing the boiler efficiency. Flue gas control. Flue gas control in a boiler refers to the process of monitoring and adjusting the composition and temperature of the exhaust gases flue gas leaving the boiler to optimize combustion efficiency, minimize emissions, and ensure safe operation, typically achieved by regulating the amount of combustion air supplied to the burner based on real-time flue gas analysis data. Flue gas analysis. Regularly measuring the composition of the flue gas, including carbon dioxide CO2, oxygen O2, carbon monoxide, and nitrogen oxides NOx, to determine the combustion efficiency and identify potential issues. Excess air control. Adjusting the amount of combustion air supplied to the burner to maintain an optimal level of excess air, which is necessary for complete combustion but should be minimized to maximize efficiency. Flue gas temperature control. Monitoring and regulating the temperature of the flue gas to ensure proper heat transfer and avoid excessive heat loss. Improve boiler efficiency. By maintaining optimal combustion conditions, flue gas control can significantly increase the boiler's thermal efficiency and reduce fuel consumption. Feed water temperature. A steam boiler plant must operate safely, with maximum combustion and heat transfer efficiency. To help achieve this and a long, low-maintenance life, the boiler water can be chemically treated. A higher feed water temperature directly improves boiler efficiency by reducing the amount of heat needed to convert water into steam, resulting in less fuel consumption and better overall thermal performance. Essentially, the boiler doesn't have to work as hard to heat the water to the desired temperature when the feed water is already hot. Freedom from scale. If hardness is present in the feed water and not controlled chemically, then scaling of the heat transfer surfaces will occur, reducing heat transfer and efficiency, making frequent cleaning of the boiler necessary. In extreme cases, local hot spots can occur, leading to mechanical damage or even tube failure. Freedom from corrosion and chemical attack. If the water contains dissolved gases, particularly oxygen, corrosion of the boiler surfaces, piping and other equipment is likely to occur. As the feed water temperature increases, the boiler efficiency generally increases as well. Reduced fuel consumption. Higher feed water temperature means less heat is required from the fuel to reach the desired steam temperature, leading to lower fuel usage. Heat recovery systems. Utilizing heat recovery systems like economizers, as well as feed water heaters to preheat the feed water is a common method to improve boiler efficiency by raising the feed water temperature. Condensate recovery. Condensate recovery significantly improves boiler efficiency by allowing the reuse of hot condensate as feed water, which means less energy is needed to heat the water to its boiling point, resulting in reduced fuel consumption and increased overall boiler efficiency. In some cases, this can lead to, when condensate is recovered and returned to the boiler, it carries a significant amount of latent heat which can be reused to generate steam, reducing the need for additional heat input from fuel combustion. A 10 to 20% reduction in fuel requirements. Factors affecting condensate recovery efficiency. Condensate piping design. Proper piping layout and insulation are essential to minimize heat loss during condensate transport. Condensate collection system. Efficient collection of condensate from all steam-using equipment is crucial. Condensate treatment. Treating condensate to remove impurities can improve boiler water quality and prevent issues. Combustion air temperature. A higher combustion air temperature directly increases boiler efficiency, as the preheated air contributes more heat to the combustion process, resulting in less heat loss through the flue gas and a higher overall efficiency. Typically, a 40 degrees Fahrenheit increase in combustion air temperature can lead to around a 1% improvement in boiler efficiency. An often stated rule of thumb is that boiler efficiency can be increased by 1% for each 15% reduction in excess air or 40 degrees Fahrenheit reduction in stack gas temperature. Boilers often operate at excess air levels higher than the optimum. Key points about combustion air temperature and boiler efficiency. Heat transfer. When combustion air is preheated, it enters the furnace at a higher temperature, leading to more efficient heat transfer to the water within the boiler. Reduced flue gas temperature. By utilizing more of the heat from the combustion process, the flue gas leaving the boiler is cooler, minimizing heat loss up the chimney. Excess air control. Proper air preheating can help optimize the air-to-fuel ratio, reducing the need for excess air, which can lower efficiency. How to preheat combustion air. Air preheaters. Most modern boilers use a dedicated heat exchanger to preheat the combustion air using the heat from the flue gas. Steam coil air preheater. SCAF. Regenerative air preheater. Fouling of heat transfer surface. Fouling of a heat transfer surface in a boiler significantly reduces its efficiency by increasing the thermal resistance, which hinders the transfer of heat from the combustion gases to the water, ultimately requiring more fuel to achieve the desired steam production. This results in higher energy consumption and increased operating costs. Key points about fouling and boiler efficiency. Reduced heat transfer coefficient. When a fouling layer builds up on the heat transfer surface, it acts as a thermal barrier, lowering the rate of heat transfer and decreasing the heat transfer coefficient. Key points about fouling and boiler efficiency. Increased thermal resistance. The fouling layer adds additional resistance to heat flow, making it harder for heat to move from the hot gases to the water, impacting the overall heat transfer process. Higher fuel consumption. To compensate for the reduced heat transfer due to fouling, the boiler needs to burn more fuel to reach the desired steam temperature, leading to higher energy consumption. Local hot spots. Fouling can create uneven heat distribution on the heat transfer surface, leading to potential hot spots that can damage the boiler components. Factors contributing to fouling in boilers. Water chemistry. High mineral content in boiler water can lead to scale formation on the heat transfer surfaces. Fuel impurities. Ash and other particulates from the fuel can deposit on the heat transfer surfaces. Operating conditions. High boiler water temperatures and slow flow rates can promote fouling. How to mitigate fouling in boilers. Water treatment. Properly treating boiler water to remove minerals and control pH levels. Fuel quality control. Using fuel with low ash content. Optimized operating conditions. Maintaining proper flow rates and operating temperatures. Regular cleaning. Implementing scheduled cleaning procedures to remove fouling deposits. Blowdown. A blowdown operation on a boiler, while necessary to remove impurities and maintain proper water chemistry, can negatively impact boiler efficiency if done excessively, as it essentially wastes heated water and energy by removing a portion of the boiler water, which needs to be replaced with fresh, cold-feed water. Therefore, the optimal blowdown rate is crucial to balance cleanliness with energy conservation. Key points about blowdown and boiler efficiency. Negative impact of excessive blowdown. Too much blowdown leads to significant energy loss due to the constant need to heat up fresh feed water to replace the blown down water, thereby reducing overall boiler efficiency. Importance of controlled blowdown. Maintaining a proper blowdown rate based on factors like water quality and boiler operation ensures that only the necessary amount of water is removed, minimizing energy loss while still preventing issues like scale formation and carryover. Impact on steam quality. Improper blowdown can also affect steam quality by allowing too many impurities to enter the steam system if not managed correctly. This is end of steam generator lesson. Thank you to watching. Thank you to watching Shoaib Views channel. If you like my videos, kindly subscribe, like, share and follow my channel.